What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to introduce the idea of domain. What is the domain of a function and how do we find the domain of some basic examples? That's what we're going to go through in this video. So it's an introduction and I hope this helps you. What's the domain of a function? It's the set of all inputs that produce real number outputs. So functions have inputs and outputs. This linear function, for example, inputs are x values, stuff we plug in. Outputs are values of f of x. We often think of them as y values because we graph them on the y-axis, right? So we have inputs and outputs, and we're thinking about what are all the possible inputs? What are all the different possible numbers we could plug in to this function that would give me a real number output? And it turns out that if I take a real number and multiply it by 2 and then subtract 3, which is exactly what this function does to an input, right? Multiply by 2, then subtract 3, I get a real number. Right? So any real number produces a real number output for this function. And we can see this graphically by noticing that for any x value I pick, let's say x equals 2, boom, it corresponds to some point on the graph. It has a corresponding y value or output. 3, boom, 4, boom, even the ones that are off the screen here, right? There's no jumps, holes, asymptotes, gaps, breaks, anything like that. So what we can say is that since any real number produces a real number output, the domain is the set of all real numbers. Let's go ahead and write that out. All right, so here's how we can express the domain in words as the set of all real numbers. We can also express it using a symbol. We draw a fancy R, so 2 vertical lines and then draw an R shape through it like that. This represents the set of real numbers, okay? So we have in words, we have using a symbol. Now let's use a couple different notations. We have set builder notation. That's the one here with the curly brackets, curly braces, whatever you want to call them. And we could say x such that, what does the property x have to have? Well, it has to be a real number. This little c with a line through it means and is an element of or belongs to the set of. And then we draw this fancy R here. So that's how we can express this in set builder notation. Let's see, what else can we say? We could also express it on a number line. Right? I can draw a number line. This number line represents all the real numbers. And so what's the domain? Well, I'm literally just shading in the number line, right? So this isn't that interesting of a representation since the domain is the set of all real numbers. But when it gets more complicated, this is actually going to become really helpful. And finally, I have interval notation, which is all the numbers from negative infinity all the way up to positive infinity. So total, we have 1, 2, 3, 4, 5 different ways to represent this domain of this function, which is the set of all real numbers. All right, let's look into a couple more examples. Think about what are the inputs I can plug into this function that give me real number outputs. Are there any numbers I can plug in that don't give me a real number output? The answer is no. If I square a real number, the result is a real number. If I cube it, if I multiply by 2, if I make it negative, all these things produce real numbers, and we can see this graphically, again, by looking at their graphs and noticing that every possible x value corresponds with some point on the graph. Even though it seems like it's going up forever, -4 does line up with some point off the screen, right? Same here with 5. It lines up with some point up here on this function. And so what we've noticed is we've seen 3 examples now that all have the same domain. They all have a domain that's the set of all real numbers. And in general, any linear function, quadratic function, or polynomial function has a domain that is the set of all real numbers, which we've seen different ways to express. The only exception is when we use these functions to describe some kind of real-world context or situation. Sometimes in those cases we want to restrict the domain so that it makes sense in the context, and we will see an example like that at the end of this video. But in general, these have no domain restrictions. Domain issues, problems, that's how they're often described. So we're good to go, linear, quadratic, polynomial. Now let's get into the exciting stuff. What are examples of functions where I can plug a number in and I won't get a real number out? And this is one of them. What happens when I plug 2 into this function? F of 2. In the numerator, I get 2 plus 1, that's 3. In the denominator, I get 2 minus 2, that's 0. A fraction we can think of as representing division. This is 3 divided by 0, right? So this is undefined. We can't divide by 0. Undefined. So what we just found was a number that we could plug in as an input, but it didn't produce a real number output. Undefined is not a real number. It's not a number at all, right? So 2 cannot be in the domain of this function. It can't be in the domain of this function, okay? And in general, one way to think about this is nothing that makes the denominator 0, because remember, a fraction is like division, nothing that makes the denominator 0 can be in the domain of this function, right? And so this is what we often call a domain restriction. We took the denominator and we set it not equal to 0. This can't happen. And what we do is we can add 2 to both sides and say x cannot equal 2, which is what we just determined here, right? X cannot equal 2. So maybe I'll go a step further and I'll write that. This is the domain restriction. X cannot equal 2, and we got that by setting the denominator not equal to 0. This is the domain restriction. So how can we actually write the domain of this function? We could say, well, that's the only problem here, right, is 2. Any other real number gives me a real number out. There's no other way to make x minus 2 equal 0. So the domain is the set of all real numbers except for 2. Let's go ahead and write that out. And now let's see if we can express this in a few other ways. So let's go back to maybe our set builder notation. So curly braces, we could say x is a real number such that, what condition? Well, x cannot equal 2. So we're just placing that restriction into this condition that has to be true for these x values in this set. So that's how we can express it in set builder notation. What about on the number line? Let's draw a number line here. Arrow, arrow. So how do we represent all real numbers except for 2 on a number line? Well, we can draw an open circle at 2, excluding it. Include everything bigger than 2, that's to the right, and include everything smaller than 2, that's to the left. And finally, we can write interval notation, which is actually easy if we do our number line first. And this is how I teach kids to write the domain of a function in interval notation, is first to write it on a number line, because now we can see that this little section corresponds to this interval from negative infinity to 2, right? That's this piece here. And then union, and we're picking back up after 2. So we're just excluding 2. We're just skipping over it. And so this is broken up into 2 pieces like this, so we have 2 intervals. Awesome. So these are all different ways to express the domain. We got 4 different ways. We understand the idea of a domain restriction. We can't divide by 0. And this is what happens graphically. So when we have this division by 0 with rational functions, it looks like one of 2 things. In this case, we have an asymptote. In some cases, it could just be a hole in the graph. That's also a thing. So you could just see a hole. Oops, bad color to use there. Could just see a hole like this, right? So just a little tiny missing piece where the function's not defined. Okay, so every other real number works. It's just 2 that's the problem. That's why we had the restriction. And now let's try another example here. What's the issue with this example? What type of numbers can I plug in that would give me not a real number output? So again, that's kind of how we're thinking when we're finding domain. It's not what numbers give me real numbers, because there's usually infinitely many, and that's usually kind of hard to think about. It's often better to think about what numbers create problems, what numbers don't give me real numbers. So one of those cases is dividing by 0, and the other case is actually complex numbers, negatives under square roots. So for example, if I plug 2 into this function, f of 2, I get the square root of 2 minus 3, which is the square root of negative 1. This is a complex number. It's not a real number. So different from undefined, it is a number, but it's not real. And so 2 is not in the domain of this function. What about f of 0? Right? Because in the last example, we just saw one number we had to exclude. But what about this example? F of 0 is square root of negative 3. That's not real either. Well, we know there's at least 2, and actually it's going to turn out that there are infinitely many problems. So how do we figure out which of these numbers create problems? Well, we could instead think about, well, what numbers are we allowed to have? What numbers under this square root would produce real number outputs? And what can be under a square root is 0. The square root of 0 is 0. That's a real number. And anything positive, the square root of a positive number, is a real number, not a complex number. So our domain restriction here is x minus 3 has to be greater than or equal to 0. Okay. So if we were to add 3 to both sides, then this would be our domain restriction. This is how we would want to write it. Domain restriction is that the x values, the inputs, have to be bigger than or equal to 0. So let's describe it in different ways. What's the domain of this function? So I could say the set of all real numbers greater than or equal to 3. That's one way to write it in words. Okay, I can write set builder notation. So I can say x is a real number such that x is greater than or equal to 3. So this is what kids often like about set builder notation is they don't have to do anything new. They can just write x is a real number such that and write the restriction. That's what we did last time too when x did not equal 2. So kids often find that's the easiest, but interval notation is the most common. Let's draw a number line. How can we say greater than or equal to 3 on a number line? Well, if 3 is here, then we want to fill this in to say it's part of the domain. It's part of the set. And then greater than would be going this way, right? And this aligns perfectly with our interval notation, which when we're filled in like this, we use a bracket. We want to include 3 in the set, and then we get bigger forever and ever. And so here are 4 different ways to describe the domain of this function, and we could see what this kind of restriction looks like on a graph. And we should be familiar with graphs of radical functions. 3 is the smallest x value, right? That's why the domain is x greater than or equal to 3. Every number bigger than 3 is represented in the domain. So we just see this abrupt kind of stop. Nothing exists past there. That's what this kind of restriction looks like. So let's summarize what we've done so far. There are 2 primary ways for an input to produce an output that is not a real number. One is it could cause division by 0. We have 0 in a denominator. Remember, a fraction is division. So 0 in a denominator means division by 0. That's bad. That's undefined. Okay. The other way is negatives under square roots. And actually, I want to mention, or any even root. If we have a 4th root, 6th root, 8th root, all those even roots are going to give us complex numbers when they have negatives under them. The odd roots actually will give us real numbers. Okay. For example, the cube root of -8 is -2. You can cube numbers and get negatives, but you can't raise them to even powers, so that's the issue there. So what are we going to do knowing each of these issues? And by the way, if you know this, literally 95% of domain questions you can solve. If you know this and you apply this appropriate strategy, which is first, we're looking for variable expressions in a denominator. Why? Because that's when we potentially could have a denominator that could equal 0 at some point for some variable. So we identify those variable expressions and we set them not equal to 0. That gives us the restriction. We also look for variable expressions under a square root or any even root. That's when we have the potential to have a negative under a square root or even root, right? So we're identifying those and we can get the restrictions by setting the expressions greater than or equal to 0 and solving. So let's jump into some more examples here. Let's look at these 2. F, you should be able to tell me the domain of it by looking at it. It's kind of tricky though. What kids often do is they say it's a fraction and then they try to do a bunch of stuff, not noticing that in the denominator there is no variable. This is actually a linear function if you break up the dividing by 5. You can write this as 1/5 x, right? This is equal to 1/5 x minus 1/5, linear function. So again, key idea here, variable expressions in a denominator. This is fixed. 5 is in the denominator. There's no way to divide by 0 because the division by 5 is fixed. Okay. Similar idea here. The square root's present. Kids think, oh my God, what's the domain? There's a square root. What's the rule again? Well, this is just square root of 2. It's fixed. There's no way for me to have a negative under here. It doesn't change. The variable expression is here, and that's square. That doesn't give us any domain issues. So these each have a domain of all real numbers. Hopefully that's making sense. Okay, so again, going back to this strategy, we're looking for variable expressions. And we're setting those either not equal to 0 if they're in a denominator, or greater than or equal to 0 if they are under a radical. All right, let's try this example. So again, I'm looking for variable expressions in a denominator or under a square root. This doesn't have any square roots, but it does have a denominator. The denominator could equal 0 for some value of x. So I want to exclude that value or values by writing this. This is my domain restriction. And now I just need to solve for x. 2-step linear equation. I'm going to add 5 to both sides. And so I get 3x cannot equal positive 5. And then I'm going to divide both sides by 3. And I get x cannot equal 5/3. So what's my domain? Let's express it in all the different ways. Okay, the domain of this function f In words, what do we have? All real numbers except for 5 over 3. When we solve this equation, there are no other fractions, no other denominators. That's the only restriction. That's the only real number that gives us not a real number output, division by 0, right? Undefined output. So we can say the set of all real numbers except for 5/3. Let's write that out. All right, now we can express it in set builder notation. This is typically students' favorite because we just write x is a real number such that x does not equal 5 over 3. And there's actually some kids that hate this. It's a very vocal minority because they have to learn new symbols and they hate that. So they just do interval notation, which I secretly like because interval notation is goated. It's the best. So let's go and write our number line here. How are we going to express this on a number line? Here's all the possible real numbers. How do we demonstrate or show all of them except for one? Well, we just put a hole and we fill in everything less than it, everything greater than it. Okay, so that hole right there is at 5/3, and that's how we can show this on a number line. And finally, that lines up with our interval notation, which is why I like the number line approach here. And we get negative infinity to 5/3 union. By the way, I wasn't explicit about what that U means. Union 5/3 to infinity. Awesome. All right, we express the domain in 1, 2, 3, 4 different ways. Let's try another example. All right, first we're looking at the graph. Boom, we got the asymptote at 5/3. That's what it looks like. Now we're trying the other example. Awesome. Here we got a square root. I wanted to show this example because kids freak out. What do I do with the 2? What do I do with the -1? All we care about is what's under the square root. We want what's under the square root to be greater than or equal to 0. Okay, so that's going to be our domain restriction. So our restriction we're going to get, because there's nothing in a denominator, there's no variable expressions in a denominator, there's just something under a square root. And what do? Well, we want that to be bigger than or equal to 0. If it's less than 0, then it's a complex number, not a real number. So we're going to set it greater than or equal to 0. We can subtract 3 from both sides. We get x is greater than or equal to -3. And that is our restriction. Let's go ahead and circle it. This is our domain restriction. X is greater than or equal to -3. So let's express the domain in a few different ways. And by the way, this trips kids out a lot too. Wait a minute. X is bigger than or equal to -3. You said x values can't be negative when we're dealing with square root functions. Well, it's not the x values that can't be negative. It's the entire expression under the root that can't be negative. When I plug in -3 to this function, I get 0, and the square root of 0 is 0. And when I plug in anything bigger than -3, I get a number greater than 0. I get a positive number under the root, right? So it's not the x values that need to be non-negative. It's the entire expression under the root. All right, sorry, tangent. The domain of f. All right, in words, let's express it. What are we going to write? The set of all real numbers greater than or equal to -3. All right, so we got it expressed here in words. What else do? We can do set builder notation. X, let's see, is a real number. There's different ways to write this, by the way, such that x is greater than or equal to -3. Boom. There's our set builder notation. Let's do our number line. Number line. How do we express all the numbers greater than or equal to -3 on a number line? Well, we include -3, so we want to fill that in, and then greater than, so we want to go this way. Boom. Greater than or equal to -3, and that corresponds to this in interval notation, -3 all the way to infinity. So 1, 2, 3, 4 different ways to express the domain of this function. And here's the graph. Boom. Again, with these square root functions, we're just abruptly starting somewhere. We can sometimes have it flipped as well. You will see examples like that where x has to be less than or equal to some number. Kind of trippy, but that is a thing. And finally, let's go to our last example. I mentioned this earlier. Sometimes the domain of a function that models a situation is restricted so that it makes sense in the context. So let's look at this example. We have a function that models the height of a soccer ball in feet t seconds after it's kicked. Okay, this models the height of a soccer ball. So what is a reasonable domain for this function given the context? We want this function to model this situation. What is a reasonable domain? So we're thinking about what values for t do we want to allow? Well, if it models, let's see, what is it? T is seconds, right? And it models height. The y value is height. So if t is seconds, would it make sense to have negative time? What would that even mean? Probably wouldn't make sense, right? And if we did have negative time, like time before the ball was kicked, this certainly wouldn't model it. These are negative y values. So for this function, we probably want to start at 0. We probably want 0 to be the smallest input for this function. And what about here? This is where the ball hits the ground again, right? Goes up, reaches a maximum height, hits the ground. And then it's saying the height goes negative. What would negative height mean? I don't think that makes a lot of sense. So I think probably the most reasonable way to restrict the domain would be to make 0 the smallest input and make 4 the biggest input. And there's two different ways we could write that. We could say t is a real number such that 0 is less than or equal to t, which is less than or equal to 4. Sandwich it like this, or using interval notation with brackets. And this seems like the most reasonable way to restrict this domain so that it accurately models and fits this context. Awesome. That's the last problem I got for you. Hopefully this video helped. If it did, like the video, leave comments with any questions, check out my channel, check out my playlist to get more help. Subscribe to support me, do all that stuff. But most importantly, keep flexing those brain muscles, and I'll see y'all later.